Welcome to this week's Rough Cut. Before I get started, I just want to announce and remind you all that it's IOE Friday at Bridger Brewing. Come on over at 5 o'clock. A bunch of us will be there. We can celebrate the end of the semester. Everybody's invited. Bring your students. We don't buy the beer. So I'm happy to introduce our newest faculty member, Rich Reddy, who has been here now 2 weeks? 3 weeks in the Ag, Econ, and Economics Department. He came from Penn State, where he was in the Ag, Econ, and Rural Sociology Department for 15 years. And before that, he was a visiting professor at the Ag University of Norway, OS, you can tell you how to say it, AAS. And he was there for 3.5 years. Before that, he was assistant professor at University of Kentucky, and then an economist in the Office of Policy Analysis for the Department of Interior. So he has this broad array of experience in government and U.S. and international areas. His specialty is people and groups and how they use and benefit from the services that ecosystems provide. And his focus has been on climate change, invasive species, outdoor recreation, and landscape change. So turn it over to you. Thank you.
Thanks. Well, I'm really grateful to be able to come and give a presentation soon after I get here so people can get to know me and get to know what I do, and we can start exploring different collaborative opportunities. What I want to talk about today is a kind of a way of thinking based in economics that helps us think about how people make decisions and what determines their behavior, and then what we can learn from looking at the decisions people make. So just some examples of environmentally related decisions that people make. I'll talk a little bit about how farmers make decisions about what crop to plant. And then we can, if we understand a little bit about that, we can maybe look and see how they might adapt to climate change, for example. Should I use irrigation, what crop, that kind of thing. Outdoor recreation, I'll talk about some applications in outdoor recreation. How often do I want to go out and do things? What kinds of activities do I want to engage in? Where do I want to go? Those are kinds of things that could be affected by environmental quality and affected by climate change. The third example that I have a picture of is another area I've worked on I won't talk about today, is land conversion. You know, if I'm a farmer, how do I decide whether or not to continue to farm? Should I sell out to a developer? Those kinds of decisions. So what I want to do today is just, first I'll talk a little bit about choice modeling, give you a little feel for kind of the way we think about choice modeling as economists. Then I'll go through 3 different examples where we use choice modeling in specific applications, and then try to wrap up with some kind of lessons learned from different applications. And that should kind of maybe suggest people start thinking about where this could be applied in your own work, and so that we can talk about collaboration. All right, well, before I start talking about human behavior, I'm going to talk a little bit about choice modeling in the context of animal behavior. Before I was an economist, I was a fisheries biologist. And I spent a lot of time cutting up young of the year yellow perch, like in the picture on the left, under a stereo microscope to see what they ate, right? So, and these fish feed on plankton. So the picture on the right shows a variety of plankton. And what you find when you do this enough is that you tend to find some fish that are packed full of small plankton, like the copepods, or the smaller plankton in the right-hand picture. Lots and lots and lots of little copepods. And you see some fish that are packed full of larger plankton, like the large Daphnia on the right-hand side. There'll be fewer of them in the gut, but they'll still be equally full. And you'll see that combination. You'll see both types of fish that were collected at the same time that were feeding in the same water. And this doesn't seem to be just the extreme tails of the distribution. There seems to be, it looks like fish are choosing one of two strategies. Should I target small prey, which are more abundant, in which case I don't have to swim as fast. I can just kind of slowly swim around. I'll see a lot of these things. I'll eat a lot of them, but each one I eat will give me less nutrition. Or should I swim faster and seek out the big prey, right? There are two different strategies. So we can call this the copepod strategy and the Daphnia strategy, right? The copepods are the small ones, the Daphnias are the large ones. So then from the perspective of the fish, which strategy should I choose, right? This is a choice problem, right? And so as an economist, we look at this and we say, well, we have a way of thinking about this. Actually, ecologists have been looking at these kinds of problems for a long time as well, and there are certainly papers in the fisheries literature that take this exact approach. So as an economist, we would say that the fish has a choice set that has two options, right? Two strategies. You pick one strategy or the other strategy. How do you make that choice? Well, from the perspective of a fish, a young fish, what it wants to do is it wants to maximize its net caloric intake. Right? It wants to get as many calories as it can, as fast as it can, so it can grow up big enough to get past its critical period. So the net caloric intake is going to depend on how often you see a prey item, right? The F, the frequency of encountering, the probability of successfully eating that prey item once you find it, right? Sometimes you miss, and then the calories you get per prey item, and that would be your intake of calories, right? And then you also have to worry about the energy that you're spending swimming, because the Daphnia strategy, you're swimming faster, you're using up more calories to follow that strategy. So then the question becomes, which of these strategies gives you a higher net caloric intake? So that's the way that the ecologists look at this. As economists, we can extend this a little bit more, and we can say, what if there are some things about the strategies that we as the researcher can't measure, right? So one example, you could call that tastiness of the prey. And tastiness could have lots of different dimensions. I've got a picture of a spiny water flea. The flavor might be fine, but it might be very uncomfortable to eat that prey item. So there are things about the prey that are not incorporated into net calories that the fish may care about, right? Nutritional content, for example.
Don't mind me.
Okay. So economists have this concept of utility. And utility simply means kind of the payoff. It's a measure of of your kind of net payoff from following a strategy. So we can add this extra term T, which captures all of the things that aren't captured by net calories, right? Nutritional content, discomfort from swallowing, all those kinds of things. We can't measure T, right? That's the point here. But we can learn something about T by looking at what fish do, right? So if you put fish in a tank and they're filled with Daphnia and spiny water fleas, and you see that the fish eat the Daphnia and don't eat the spiny water fleas, then you know there's something about the spiny water fleas. You can calculate the net caloric intake from eating spiny water fleas, but if they don't do it, there's something about spiny water fleas the fish don't like, and we can measure that. We can measure the difference in the attractiveness of the two, right? We're going to follow a similar strategy in looking at human behavior, right? A couple of important points which will carry through to when we think about human behavior. First, in this context, not every fish follows the same strategy, right? And as I started out saying, you see some fish that are filled with large prey, some fish that are filled with small prey. So we have heterogeneity among fish and their preferences, right? And we see that in humans as well. The second point is, you can take the same fish, put them in the same tank with the same type of prey, and it might follow two different strategies on 2 different days, right? We'll see that with humans as well, and we call that random utility. There's a random component to utility, right? All right, so that'll show up again. All right, now let's move one step up the food web and look at angler behavior and think about it in the same way that we thought about the fish behavior, right? So let's take a very simple problem. We have a person who decides he or she wants to go fishing and thinks, where should I go fishing? right? I have two options. Let's keep the choice set very simple. I can go to a close by site, which is easy and cheap to get to, but the quality is not so high. Or I can go to a farther site, more expensive to get to, but it's going to give me higher quality. However quality is measured. Catch rate, scenic beauty, however you're going to measure it. We can put together a model of how they make that decision. And this model is going to, let me use the mouse so that people else, there we are. So V here is the utility that you get from a particular site. Here we have two sites, C for the close site, D for the distant site. You get a level of utility from each of those two sites that depends on the quality of the site. Oh, there it is. It goes away very quickly. The quality of the site and depends on the costs of accessing the site, which we'll measure as the travel costs. And those costs include not only the gas and wear and tear on your car, it also includes your time. Time spent traveling also has a cost, and we can accommodate that. So epsilon here is a random term. That's why we call these random utility models. Each option has a random component to its utility, right? We don't get to measure those. Then finally, the last two pieces of this equation, there's the equation shown again in more general form. The last two pieces are the parameters, and these are what we call these preference parameters, right? So alpha is the additional utility you get from an increase in fishing quality if you go to the site. If we improve the site, it would make the utility from that site higher. Beta is the disutility you get from spending money getting to the site, right? So beta you can think of as the utility associated with money, right? Now, an angler will be willing to drive farther to get to a better site as long as the additional utility from the higher quality, which is alpha times the change in quality, is bigger than the additional disutility from spending more money getting to the site, which is beta times the change in travel cost, right? So as long as the left-hand side of that inequality is greater, you'd be willing to go to the more distant site, right? Now, we can take that behavioral response and learn something about what you're willing to pay for an improvement in quality. And it turns out that you would be willing to pay up to the ratio of alpha over beta to get a 1 unit increase in quality at the site that you chose, right? So we call that your marginal willingness to pay, right? The amount you're willing to pay for a marginal increase in Q. And this is where we get to the value of ecosystem services. If we change the quality of the site, that's worth something to the people who fish there, and this alpha over beta gives us a measure of the value that people place on a change in quality at the site, right? So when we get to so when people talk about valuing ecosystem services, in this model, that's where it's coming from. All right, now, this model, this random utility model, is really a workhorse in economics, and it's largely because of this result, which Daniel McFadden found published in 1974. He got a Nobel Prize for this and other things. What he found was that in this model, if you make a specific assumption about the distribution of the random error terms, then you can calculate the probability of choosing each site using a fairly simple formula, right? And it depends on the utility. You can see what you take is the deterministic component of the utility, which is the utility that excluding the random error term. And sites with higher expected utility are more likely to be visited. Sites with lower expected utility are less likely to be visited. It's a fairly simple formula. With this formula then, we can look at behavior and we can choose values of alpha and beta where the model seems to match the observed behavior. So if we see lots of people making choices, we figure out values of alpha and beta where the model predictions are consistent with the choices that people are making. Right? So we could technically what we do is we use this to construct a likelihood function, and then we choose values of alpha and beta that maximize that likelihood function, right? Now we have values of alpha and beta, we can do lots of neat things. We can predict what would happen if quality changed, how would that change behavior, how many more people would go to one site, how many less people would go to another site. We can use that ratio alpha over beta to value that change in quality, right? Okay, so that gives you a little bit of an idea of how choice modeling works. Now I'm going to go through 3 different examples where we've used it. The first is, again, a recreational angling example. I talked about this when I was here last year. So this was I'll just briefly go through some of the specifics here. This was a study that was done as part of the Great Lakes Mississippi River Interbasin study done by the Army Corps of Engineers. They were looking at the question of whether or not they should close the locks on the Chicago River that connect Lake Michigan to the Mississippi River drainage. And they wanted to know, they wanted a model of how recreational anglers behave so that they could look at what impact invasive species might have on recreational angling. So what we did is we did a survey of anglers living in this entire study area that's shown here. We did about 3,500 completed surveys that covered about 100,000 trips that anglers took. And for each trip, they told us where they went to the county and what type of fishing they did. We had 7 different types of fishing, right? So it's a fairly complex choice set here. We had something like 1,000 counties they could visit. We had 7 different fishing types they could engage in. So each person, every time they woke up and decided, should I go fishing today, they have a very rich array of possible places to go fishing and types of fishing to engage in, right? So to make this a little more structured, we set up the statistical model in a way so that there is some sort of sequence to how the decision is made. The first decision that they make is, should I go fishing, right? Or should I stay home and do something else, maybe go to work? Once I decide to go fishing, then I pick the type of fishing I'm going to do. And the 7 types are fishing for cold water species in the Great Lakes, fishing for warm water species in the Great Lakes. We have warm water and cold water species in inland lakes, warm water and cold water species in rivers and streams, and then anadromous, fishing for salmon and trout on anadromous runs. Once you decide which fishing type you're going to engage in, then you decide where you're going to go, right? And the probability of doing a particular type of fishing depends on the quality of the sites that are available that offer that type of fishing, right? So the lower decisions feed back up to the upper decisions and influence the upper decisions, right? So someone who lives in Michigan may make very different decisions about what type of fishing they're going to do than someone who lives in Missouri. All right, so now I won't go through this in a great deal of detail, but the point is we have this utility function, very similar to what I showed you before, but with more details. Here we have lots of different characteristics of the sites. These are the cues in the model I showed before. Now we have lots of different cues, and the cues vary depending on what type of fishing you're going to do. So a measure of quality that's relevant to salmon fishing in the Great Lakes might not be relevant to bass fishing in a river, for example. Right? So we have different quality measures for different types of fishing. We have travel cost. Beta in this case should be a negative number because travel cost is a bad thing. Higher costs are worse. We have characteristics of the angler. Those can influence utility in a way that determines whether or not you go fishing and what type of fishing you do. And then the piece that was really critical for us was the catch rate. This is our measure of quality that could be affected by invasive species. This was the thing that the Army Corps was most interested in. So this catch rate index was calculated, and we wanted to see, was there a behavioral response to changes in catch rate. Okay. All right, so just jumping to the results, what did we find? Quality of the sites did affect people's behavior, right? People do respond to quality. For inland lake fishing, the more lakes you have in a county, the more likely it is people will go fishing in that county on lakes. The more stream miles you have, the more likely it is people will visit that county to fish on streams and rivers. Higher water quality, counties with better water quality had more visitation. People were more likely to go fishing in those counties. People were more likely to go fishing if there was higher catch rates, right? As catch rates decrease, visitation decreases, right? And then finally, people are more likely to go fishing close to home than far away from home, right? So every one of those is a reasonable result. It's nice to see that people actually behave in predictable ways, and we can detect those, and we can estimate these parameters associated with all these different qualities, these marginal utilities, so that we can say, for example, what impact does a change in catch rate have on behavior, and what impact does that have on the value that people get out of fishing, right? On the catch rate, one of the interesting things we found is that the Great Lake cold water anglers, so these are the people fishing in the lakes for salmon and trout, mostly lake trout, were the most sensitive to catch rates. Those were the ones who decreased their visitation the most in response to a catch rate. Anglers who were targeting anadromous runs were the least sensitive. There's something about people who fish anadromous runs that they are going to go fishing no matter what, right? And they're going to, that's what they love and that's what they do, and they're going to, as long as there's one fish to catch, they're going to be out there looking for it, right? So we can use these kinds of models to ask what-if questions. So there's a picture of a, I think that's a Chinook salmon caught in Lake Michigan, to give you an idea of kind of what this resource looks like. So we, for example, ran a scenario where there was a 25% reduction in catch rate for all salmonids in the Great Lakes and in anadromous runs from the Great Lakes. We said, how will people respond to that, right? Our model can tell us. It'll tell us that a 25% reduction in cold water fish in the Great Lakes gives us a 34% reduction in fishing days for cold water species in the Great Lakes. So there's more than a one-to-one response for cold water for this type of fishing, fishing off of a boat for salmon and lake trout. Anadromous runs at the bottom of the table, we have a 25% reduction in anadromous catch rates, but we had only a 14% reduction in fishing effort. Okay? So as I said, those people are going to go fishing. What this model also shows is that some of that lost effort transfers into other types of fishing. So people substitute, and the model accounts for that kind of substitution. So we see increases in the other 5 types of fishing. Right? So if we have a decrease in trout and salmon in the Great Lakes, we're going to see an increase in bass fishing on inland ponds, for example. Right? The model can tell us that. We can also, as I said, from this model infer something about what these changes in quality are worth to people, right? And this gets back to the value of ecosystems, so catch rates for salmonids in the Great Lakes. We got an average willingness to pay of that for per angler of a decrease of $12. So the hit on the average angler was $12 from that reduction. Now, you have to remember, this is an average over a very large study area. Some of the people in this study area don't really have the opportunity to go fishing for salmon and trout in the Great Lakes. We go all the way to Missouri, right? So those people had no impact at all. We're averaging over a very large area. If we look just at, say, Michigan, right, which has some of the best access for Great Lakes, we have much bigger numbers. We had the averages then would be up around $40 per angler, right? When you can also add that up over all affected anglers and get about $80 million annually would be the hit from this reduction in catch rate for salmonids, right? Okay, so this is an example of how we use choice modeling to look at what people are doing, learn something about why they're doing what they're doing, and then once we have that understanding, we can then predict how they will change their behavior in response to, say, external impacts. In this case, we're looking at invasive species, right? We could look at climate change, and if we had a reduction in, say, the area that supports trout, for example, we could see how many people would switch from trout fishing to warm water fishing, for example. And would there be an impact on total fishing, right? That's a big question right now in looking at the impacts of climate change on fishing. Yes, it's going to be bad for trout, but will people just substitute and start fishing for bass and crappie and fish and things like that? If you go to Georgia, there's not a lot of trout, but there are a lot of fishermen, right? So, you know, what's to say we won't all just become fishermen like people in Georgia, right? And still go fishing, but for different species. These kinds of models can tell us how people will respond, right? And just to kind of give you a little bit of the feel, what we find is that people go fishing, fishermen go fishing about as frequently regardless of the quality they face. Okay? People who face high quality go fishing about as frequently as people who face low quality. So changes in quality will get people to change their behavior, but they'll still go fishing, right? The bigger question is, do changes in quality chase people out of the fishery entirely, right? Which we have less information on that. We're looking at that now. All right, second example. This was a project, a graduate student I was working with did this as kind of a pilot study to see how well it would work out. We asked the question, how do farmers make decisions about what crops to plant, right? And how might that be influenced by climate change? We're working in the Mid-Atlantic region, and in the region, 3 of the most important crops are soybeans, corn, and hay. So climate change will have a couple of important impacts, higher temperatures and precipitation, increased evapotranspiration, possible CO2 fertilization effect. There's also potential changes in prices that would also influence how farmers would behave. So one of the things we're discovering is that the impact in places like Virginia and Maryland and Pennsylvania of climate change, yes, there will be an impact on how well, for example, corn grows, but probably more important will be the impact on corn growing in Iowa, right? Because if Iowa grows a lot more or a lot less corn, that's going to change the price of corn, which is going to have a bigger impact on Pennsylvania farmers than, say, changes in precipitation will, right? Well, there are 2 ways that you can model crop choice. You can use agronomic data, where you go out and do field trials and see how corn does under different climate scenarios and see how soy does under different climate scenarios. Or the way we did it is we just looked at what farmers were growing now, and we tried to relate that to differences in soils and climate. And we said, if farmers are growing corn in certain places, that must be because that's an area that's good for corn. If they're growing soy in other places, it must be that's a better area for soy, and so on. So we can learn something from what the farmers are doing about what makes an area good or bad for different crops. So how do we do this? Well, first what we did is we took the landscape and divided it up into fields, right? Now, we didn't go and trace each field. We just arbitrarily put a grid on there and made artificial fields, right? We did this from New York down to North Carolina, right? So each field was about 22 acres. We then looked at where different crops are being grown, and the National Ag Statistics Service has crop maps that they put together, which aren't perfect, but are probably as good as anybody's in saying what's being grown where, right? We overlaid our fields onto those crop maps, and what you see is that any given square has more than one crop growing in it, typically, right? So we have an allocation routine where we essentially find the type of crop that is the most prevalent in each square. And then we have to adjust that, because if you do that, if you don't do some adjustment, you underrepresent the less frequent crops. So you have to kind of bump them up a little bit to get the right totals. So now we have our artificial fields. We have one crop growing in each field, right? And it's a simplification of the real world. Now we want to be able to predict why is it that some of those squares have corn and some have forests and some have soy and so on, right? So we need the drivers. So one driver is soils, right? So we have soil maps. We can get information about the soils, and particular things we looked at were available water, drainage, capability class. We have a model of crop yield potential for the different crops based on the soils. We also looked at slopes. I don't have a picture for slopes, but that was another factor that we put in. And then we looked at climate. We used the PRISM maps to get downscaled climate information. We constructed two climate variables. One had to do with precipitation and the other had to do with temperature. So we have a temperature index that we constructed that was correlated with the growing season length, right? And we basically looked at temperature at the beginning and the end of the I think what we did is, if I remember right, is we took kind of a spring temperature and a fall temperature, took the average temperature in a spring month and the average temperature in a fall month and averaged those together, and then that would be an index that's correlated with growing season length, right? All right, now, from the farmer's perspective, which crop do you grow, right? Well, each crop gives you a different payoff, and here we're calling these payoffs economic rents. It's the same concept we had before in utility. One difference is when we talk about economic rents, we're typically measuring those in dollar values, whereas a utility is measured in numbers that really don't have any units. So these rents depend on the revenues that you're going to receive from growing the crop, which we get from our soil models, which tell us the potential yield. But then they're adjusted by slope of the field, soil characteristics, and then the climate characteristics. So we have 7 different crops that you can grow: corn, soy, small grains, hay, pasture, fruits and vegetables, and forests. The 7 different crops you can grow. So each one of those has you can think about these as utility functions in the context of what we're talking about before. But the key point here is the payoff from each one of the 7 depends uniquely, each one depends differently on climate, right? These rents incorporate not only the monetary payoff from growing a crop, but also everything else that the farmer worries about, right? So if you're a dairy farm and you need corn to feed your cows, so growing corn is more valuable to you than growing small grains, it will be incorporated into this. If a certain crop takes more of your time, say fruits and vegetables, then a different crop that's easy to grow, say hay, that'll be incorporated into these rent equations. So we now have lots and lots of fields, thousands of fields, tens of thousands of fields that we've done this for. We can then, for each field, based on the measures we have for that field, predict the probability of each of the 7 crops. And then we pick parameter values, those are the red things, that give us predictions that are consistent with what we observe. Right? And that's how we estimate the parameters of these equations. And what you find, so here's just a few, just to show you that we do get some numbers. We find that higher temperatures are good for corn, even better for soy. Hay doesn't like higher temperatures, and so on. Precipitation had less of an impact than temperature. We can take these models then to make predictions for individual fields and see how those predictions would change as climate changes. So here's an example for one field. And it shows the rent that field would generate under 3 different crops. That's what each curve shows. The horizontal axis shows our temperature index. So as temperature increases, we see that hay becomes less attractive. Corn initially becomes more attractive and then becomes less attractive. And small grains, higher temperatures are always better for small grains through the range we were looking at. So we would expect if this is a more northern field and it's facing temperatures down in this range, we'd expect it to be in hay. And if it's somewhere in this range, we'd expect that field to be in corn. And if it's over in this range, we'd expect it to be in small grains. Right? So we can do that for every field, right? And then we can ask the question, what if climate change comes in? How will that change what happens on each field? And we do this in a probabilistic way. Right? We say the probabilities change, right? Clearly, not every field in New York is in hay, and not every field in North Carolina is in small grains. So this is all probabilistic, right? So these first two examples, the recreational angling example and the crop choice example, in both cases we could see what people did, right? In the angling example, we asked people, we did a survey and said, where did you go fishing and what did you fish for? In the crop choice, it was done using remote sensing, right? But in both cases, we could see what people did, and different people face different situations. Different farmers face different climates and soils. Different anglers face different opportunity sets of where to go angling and for what, right? So that allowed us to estimate these models based on observed behavior. The question is, what do you do if you can't observe behavior that would reveal these kinds of preferences, right? Either because the people doing these behaviors, it's just we can't see it happen, or they don't face situations where they have to make choices that would influence their environmental quality. So for example, if you're living in a large part of Montana and we're interested in the value you place on air quality, there's not much you can do to affect your air quality. Pretty much everything you do, you're going to have about the same outdoor air quality. So in those kinds of situations, I can follow you around all day and I'll never know. You will never do anything that would reveal to me the value you place on air quality. What do we do if we have those kinds of situations, but we want to know something about how people value that quality? Well, the answer is we ask people hypothetical questions. Right? So we have to put people into a hypothetical situation where they have to make a decision. They have to make a choice. And that choice, based on the option they choose, affects the environmental quality they experience. Right? We want to design this choice scenario so that it does that. So by making that choice, you reveal something to us about your preferences. Now, what we have to make sure is that different people that we ask these questions face different choices. So but we're in charge. We're asking the questions. We can design these so that they vary from person to person. Right? So they can vary from respondent to respondent. Very often we ask the same respondent more than one question. So we do some experimental design so that the choices we present give us as much information as possible. Now this kind of approach has been called a lot of different things. I call it choice experiment, but it's been called contingent behavior, paired comparisons. Some people use the term conjoint analysis, though that's more often used to describe a different type of survey technique. But you'll see lots of different terms used to cover this same kind of approach. These are all examples of a method where we're relying on people making statements about their preferences. So we call these stated preference methods. Example, we did a survey in Pennsylvania about people's preferences over renewable energy, and in particular renewable electricity generation. Pennsylvania has what's called an alternative energy portfolio standard. By 2020, 8% of Pennsylvania electricity is supposed to come from renewable sources. There is a 0.5% carve out for solar. So solar has to hit 0.5%. All renewables together have to hit 8%. And the companies that provide power have to hit these targets. And so if they're not reaching them, they have to go out and buy credits on the market. Right? So the policy question here was, is 8% the right number, or should we shoot for a higher target? Right? The second, and so that was what we actually were approached by the legislature, or the research arm of the legislature, to go out and look at that question. We also, while we were doing it, we asked, are there some renewable sources that people like better than others? Right? Is it appropriate that solar, for example, has a carve out, but wind does not? So we did a survey. we did a mail survey. We targeted rural respondents because a lot of the renewable energy infrastructure is going to be located in rural areas. We mailed out about 1,600. We got a little over 50% response rate. Before I get to the choice questions, people like to see a little bit of the big picture questions. On the issue of different technologies, there was very clear preference for so-called clean technologies versus dirty technologies, right? But one thing interesting to point out about this, so hydro, solar, wind, improved efficiency, those were the most favored technologies. Waste coal, conventional coal, those were the least favored. Curiously, biomass was lumped in down with the dirty technologies in people's perspective. Now, we describe biomass, which is, in Pennsylvania, the most relevant type of biomass is taking biomass and burning it in generators, right? Not this ethanol, this is not biodiesel, this is both, wood to heat kinds of things, wood to electricity, co-firing with coal, those co-firing with oil, that's the kind of biomass we're talking about. So burning, right? Seems that people don't like technologies that involve burning things, right? The second interesting thing was that coal with carbon capture and sequestration came out a little lower than conventional coal, right? Now, but I don't think that difference was statistically significant, right? But there was not some premium placed on coal with carbon capture and sequestration, right? It didn't make it magically better than conventional coal. How much of that is, is this just Volvo driving liberals who are generating this? So we split it out by political leaning. Premium or clean technologies, but they technologies. The other big question that we asked is, do you want more of Pennsylvania's electricity to come from renewable sources? Strong agreement that yes, that people want that. A little bit lower agreement among conservatives, but still a large majority of conservatives want more renewable energy. They're willing to pay more for it. They want the state to require it, not just, there was a preference for mandatory measures instead of voluntary measures. So, and that's for every demographic group you look at, comes out the same way, right? There are differences among the demographics, but everyone's in favor of more renewable. Even people who say that global warming is not happening want more renewable electricity. Right? Okay, now to the stated choice question here. So now the respondents were presented with choices like that. So we said, all right, we're going to give you two options. Each of those two options would result in a higher standard for the alternative energy portfolio standard. They would have different mixes of 4 renewable technologies, solar, wind, biomass, and then we lumped everything else together. In Pennsylvania, the dominant other renewable is hydro. We also talked about the impact that this would have on jobs in Pennsylvania, and we talked about the impact it would have on their electricity bill and on other prices and taxes they would have to pay and things like that. So in this particular, so we always gave them the no change option and could just keep things the way they are, or they could basically buy more renewable electricity, right? So in this case, each policy, each of the 3 policies is described by 7 attributes, right? Those 7 attributes are the levels of the 4 renewable technologies, how much would be gained in jobs, how much would be lost in jobs, and the cost to the household. So each of the 3 options then has a utility associated with it that depends on those attribute levels, right? So there would be 7 of these, or 3 utilities for each choice that people make. And we had, I believe in this survey, each person made 5 of these choices, right? And then we had different people got different sets of 5. So I think we had a total of 20 different choice scenarios that people saw, right, across all the different surveys. All right? Now, from that, we can estimate those betas, right, the marginal utilities associated with each of the 7 attributes. And what we find is that among the 4 renewable technologies, wind, people like wind, gives them higher utility. People like other types of renewable, other than the 3 mentioned. Not strong preference in favor of solar or biomass, right? People like when jobs are gained. They don't like when jobs are lost. And there's a significant, the 0.64 is significantly bigger than the 0.4. So people are, the disutility from job losses is greater than the utility from job gains. That makes some sense. And then people don't like cost, right? Which also makes sense. You can, again, using that alpha over beta formula I showed early on, you can calculate how much money a typical person would be to pay for a 1 unit increase in each of the non-cost attributes, right? In this case, for solar and biomass, those numbers are small and they're not significantly different from 0. But basically, for a 1% increase, an increase of 1 percentage point in wind, the typical household is willing to pay $5 a month for that, right? Okay, now the next question we asked in this one was, does everyone have the same preferences? And the answer is no. Different people have different preferences. It's important to know the distribution of preferences. At least, if anything, from a political science perspective, you want to know what proportion of the you know, low, a weak preference in favor that everyone has is different than a very strong preference that a few people have, right? So we'd like to know something about that. There are different ways that we can model that. I think I'll skip over the details of that. This gets to those betas. Different people have different betas. How do we model the fact that different people have different betas? There are kind of, there are random ways to do that. There are more deterministic ways to do that, right? I'm just going to show you the results from one of these models. And so this is a kernel density plot that shows kind of, it's basically the distribution of willingness to pay for 3 of the renewable technologies. Biomass turned out there was very little heterogeneity in preference over biomass, right? So if I had the biomass plot in here, it would be centered right around $10 and it would be a very tall, narrow spike, right? But these 3, there was some significant heterogeneity. We could identify some heterogeneity. And the thing that really was interesting is that biomass fairly tightly clustered and fairly small willingness to pay, right? People just don't seem to like biomass that much. Wind had a group of people who liked it a lot better. Solar was the one that had the most diversity of opinion. For some people, solar was the absolute best technology. For other people, solar is the absolute worst technology, right? Now, we haven't been able to kind of dig down underneath why that might be true, but I think it's an interesting result that solar is the one that has the broadest diversity of preferences, right? Some people love it, some people hate it, right? You have to remember when we're doing this survey was when all the Solyndra controversy and all those kinds of things were coming out. So some people might view solar as just basically a giveaway to connected companies, whereas other people see it as the most technologically advanced, cleanest, least land using technology, right? So very broad diversity of opinions on solar. Okay, so that's 3 different applications where we've used choice modeling to learn something about how people make decisions related to the environment. And then we can, from those decisions, infer something about what the environment's worth to people. Other examples where we've used this, land conversion development, looking at house choice and how house choice is affected by local environmental amenities. Those were both kind of looking at observed choices. Stated choice studies, look at pesticides on produce, looking at landscape aspects of green infrastructure, home heating fuel choice, wildlife rehabilitation, done a few on surface water quality, and a couple on health impacts from air quality. So just to give you an idea, there's a fair, this way of approaching the problem is useful for a lot of different types of problems. So, having done this in a number of different contexts, what are some of the things that I try to get across to people? First, you need a situation where the choice that a person makes is affected by environmental quality that they face, and their choice determines that environmental quality. Actually, it's a better way to say it, right? So if you do one thing, you experience one level of environmental quality. If you do a different thing, you experience a different level of environmental quality, right? That's critical. Second, you need variation. You need different people facing different situations. If everyone faces the same situation, you really can't learn much, right? Behavior than to work with hyper. However, you may not find situations by However, that's not always the most interesting thing that these models will tell us. Very often, the more interesting thing that they'll tell us is how people's behavior will change as a result of whatever change you're talking about. So to me, it might be more interesting to know how a riparian stream, whether a riparian stream owner will do stream bank hardening in response to climate change, than to know that the value to that landowner of climate change is $1,000, right? So $1,000, great. But if I know that he's going to put riprap in, that's a much more important piece of information. All right, and then the last thing I'll point out is that these models don't do a great job predicting individual behavior. They predict probabilities. But if you give me if you tell me that a certain person is going to go fishing and ask me where is he going to go fishing and what kind of fishing he's going to do, in Montana it's not that hard. He's going to go trout fishing and he's probably going to do it in a river and stream. But in most places, there's no way I'm going to be able to take an individual and make reliable predictions about individual behavior. However, if you give me 10,000 anglers and say, how many of them are going to go to different places, I can do a pretty job predicting that. And then I can tell you how that would change if the resource changed, right? So individual behavior is hard to predict. Aggregate behavior we can do a much more reliable job on, right? Okay, so that's left for questions.
Curious in the scientific design of something if you have a retesting time. So like you come up with the hypothesis that at 10 degrees increase in temperature might lead to 10% less fishermen or something.
Right.
Is there a retesting stage where you say, was it really right? Because, for example, you might say, well, the unemployment was up or down and that affects something not in your model.
Right. There's been a number of validity studies that have looked at the validity of different approaches. And most of those have been done in the context of stated preference methods, because those are the ones where we have the most concerns about the validity of the responses that we're getting. And what we find is that sometimes when you ask questions, you get answers that are not very reliable, but you can do it in ways that greatly improve the reliability. So there are studies There are lots of laboratory studies where we bring people in and we say, do you want to buy a coffee cup? And then we actually sell coffee cups and we see how it compares and things like that. And you can get people to predict their behavior fairly well in hypothetical questions. There have been studies, for example, there was one in Rhode Island where they did a survey of people looking at kind of willingness to pay for improved water quality. And then there was an actual referendum. They knew ahead of time this referendum was coming up. And they found their models predicted the referendum very, very well. Right? There are test-retest studies where they do the same kind of surveys, maybe with a 5 or 10-year lag, and they find that the preferences, that the answers are very stable over time. Right? So these, that kind of research does go on, and what it finds is that it can be done in a way that's reliable, but it can also be done in a way that doesn't work very well. So the trick is knowing ahead of time whether you have a reliable model or an unreliable one. Yeah.
Have you worked with anything, let's see how I can frame this up, sort of like boiling the frog syndrome, where let's say that you go somewhere for amenities.
Mm-hmm.
Let's say it's Bozeman, and you say, oh, I love the air, low traffic, this, that, and over time, population grows,
Mm-hmm.
traffic increases, air quality diminishes, the things that originally attracted you to that area.
Right.
At some point, you track that there's a flip, like, okay, I'm out of here.
Uh-huh.
Something, the boiling the frog syndrome is,
Right.
It's happening so gradually,
Right.
you just not, that's just what
Yeah.
it is.
Yeah. What I understand, if you actually put a frog in a pan and start to heat it will jump out. It doesn't sit there and die.
How about the water, like really, the water? But you know what I mean?
Yeah, I do know what you mean. There's, so the, I haven't personally done those kinds of long-range studies. One of the things we find, which is kind of interesting, is kind of the flip of what you're talking about, is that when you talk about improvements and you ask people how they would change their behavior in response to improvements, they'll tell you, oh yeah, if it's going to be better, I'll do more of it. But they don't fully appreciate all of the new opportunities that will open up as a result of the improvement. And I'll give you an example. It has to do with food safety. When irradiated beef was becoming a thing, people did marketing studies and said, would you buy irradiated beef, right? And, it's guaranteed free of E. coli. And people said, yeah, that would be worth something to me. There was a little concern over the radiation part of it, but people said, yeah, that would be worth something to me. What they didn't think about was I could eat rare hamburgers again. They just thought about the change in risk without that adjustment in behavior, right? And then when people started to see, wow, I could eat rare hamburgers again, that was an additional, they didn't think through all of the new opportunities that were available to them. So, and I think that that's very true for a lot of the types of improvements that we're talking about. We say, well, we're going to improve, and we see this, fishing quality is going to improve. We do a pretty good job of looking at how fishermen will respond, but we don't do a very good job at looking at how non-fishermen will. Will it attract new people into the fishery? We're very bad at that, at figuring that out. So there's kind of a flip side, but yeah, as things get worse, people will react. Does experience and kind of slow, I haven't seen research that looks at that kind of long scale. So, yeah, oh, okay.
That's not short.
I'd be happy to talk afterwards. Yours is short, I'll take a short one.
In your utility function or in your red function, you were using crop selection.
Mm-hmm.
I didn't see that you had what the crop the previous year was.
No, because we didn't know. We didn't know, and that would be ideal. But because we were working with remote sensing, and those maps only come out every 5 years, and they're based on kind of pictures that were taken at different times, we really only have one snapshot. But yeah, rotations would be critical. And if you were to do this, if you could get field level data that told you, is this continuous corn or is it a corn-soy rotation, those would be two different crops, right? So full soy, full corn, or a rotation, that's 3 different options. So that's what you would want to do, but we didn't have that kind of data, at least not on the scale we needed. All right.